Thank you. First of all, I want to thank Jerry Pollack, who left yesterday, I guess, and the organizers for inviting me. I don't know who did the schedule for this lecture, and I don't know if it's an honor or an insult or a punishment for putting me at the end of where the audience is about half. Anyhow, this is my talk, and this is part of more general talk, which is about solvent in general, solvent effects on any process in aqueous solutions. Now, I will talk very briefly on four topics where the solvent effects entered, and mainly most of the people for the last 40 or 50 years spoke about the effect of the effect of hydrophobic interactions and hydrophobic solvations on these problems. And I will stress more the more recent ideas about hydrophilic interactions. Now, there is something common to these two problems. Actually, these three problems, there is something common. In protein folding, the main thermodynamic problem is what is the main driving force for moving from a space where there are many conformations into a well-defined structure. So in this process, you lose the conformational entropy. And similar problem is in self-assembly of proteins. Imagine if you have two atoms, say, of hydrogen, and they have translational entropy. Once they form a hydrogen molecule, you lose one of the translational entropies of the one atom. And in the case of a molecule like hydrogen or chlorine, the energy is more than enough to compensate for the loss of the entropy for this reaction. Now, when we have two proteins that are forming a dimer or tetramers and so on, the question is, what is the energetic part that compensate for the loss of the translational entropy of the proteins? Now, molecular recognition is more specifically how a ligand binds to a specific site or a specific site on a target. And I will show that these two have something in common with respect to molecular recognition, or finding the best location for binding or the best conformation of the two proteins or protein with DNA. Now, I want to make a comment. Usually, solubility of global proteins is not considered one of the mysteries in biochemistry. I spent about 3 years at NIH and then many summers at NIH, and I had a good friend there, Harry Saroff, who was a protein chemist. And he told me that at that time I didn't know much about all these problems. He told me that most people talk about protein folding and self-assembly of protein and so on, and how the water provide the driving force for these processes. But he told me that almost no one talks about the mystery of solubility of global proteins. And I was surprised because everyone who thought about the solubility of global protein knows why proteins are soluble in water. And the common answer to this question is that there are a lot of hydrophilic groups on the surface of the proteins, And that's what makes the interaction through hydrogen bonding with the water, which makes the solvation free energy larger and negative. So this is the correct answer, but it is not the whole truth. So I will start with this problem with the solubility. This is the general scheme of how to isolate the direct and the indirect parts of the driving force. So if we have a protein folding, and the same, I think, for the case of protein-protein association, so we can always, we can always separate the direct driving force, that is, all the forces due to interactions, both intramolecular or intermolecular forces between all the groups within the proteins, and we can. So if we have the same reaction in vacuum or in ideal gas system, and we do the same reaction in a liquid, so the difference between delta G, the free energy, the Gibbs energy in the liquid, and delta U, which is the interactions, all the interactions between the groups within the molecule, will define the solvent effects as this delta G. So this definition is the same for all the process, any process in aqueous solutions. Now, the same separation is for the protein-protein association, and it is believed that both for protein folding, protein association, I will talk about the molecular recognition. Most people believe that the hydrophobic part is the most important, and I will show you why I believe that the hydrophilic interactions are more important. But I want to start, what is that? I want to start with the solubility, the kind of mystery of solubility of proteins, which is not considered as part of the mysteries of protein folding and protein-protein association. Now, in 2005 or 2006, there was an editorial in the Science magazine where they listed about 125 big questions or big unsolved questions in science. And these two problems, the protein folding and the protein folding and protein association, or any binding in aqueous solutions, were in the list of this problem. And I think that solubility of protein is not less a mystery than either protein folding or protein-protein association. Now, I will talk about two kinds of solvent-induced effect, and two kinds, and each one hydrophobic and one hydrophilic. So we have altogether four. What is that? So if this light blue is a hydrophobic group, when it is transferred from being exposed to water into the interior of the protein, I will call this loss of solvation. So here it is solvated. It is partially solvated by the water. Here it is solvated by some kind of organic environment within the protein. Now, similarly, if we have the red one for hydrophilic, say CO or OH or NH along the protein, so here it is solvated by water, this water molecule. Within the protein, it is again solvated by the environment of the interior of the protein, and it's known that almost all the hydrophilic groups that are within the proteins are hydrogen bonded within the protein. Now, there are many hydrophobic and hydrophilic interactions. I will mention only one here. This is the interaction between two hydrophobic groups mediated through the solvent. So if you have two methyl groups, for example, there is a direct interaction between the two methyl groups, and there is a solvent-induced effect, which is mediated through the water molecules. So this I will call pairwise hydrophobic interaction. And likewise, if you have two hydrophilic groups that can interact either directly, like forming a hydrogen bond between NH and CO in proteins, in the helix, or they can interact through one or more water molecules forming hydrogen bond bridge between the two. So I will call these hydrophilic interactions only the solvent-induced part, and this I will call hydrophobic, or more specifically, pairwise hydrophobic interaction, and one can extend this to triplet and quadruplet, both hydrophobic and hydrophilic effects. Now, to give you just an order of magnitude, the loss of conditional solvation of a hydrophilic group, that is moving a hydrophilic group like CO or OH from being exposed to water into the interior of the protein, you lose about 6 to 7 kilocalories. On the other hand, if you remove a methyl group or a hydrophobic group from water into the interior of the protein, the change is negative. The loss of the solvation in water, of course, of the hydrophobic group is about minus 0.3 or 0.5 kilocalories. Now, formation of pair of hydrophilic groups, this more specifically is through one water molecules that form bridge between the two hydrophilic group, like 2CO, and the water molecule that can form two hydrogen bonds. With that, it's about between 2.5 to 3 kilocalories, whereas the corresponding pair hydrophobic interaction is about half a kilocalorie. Now, as I said, I will start with solubility of protein, and now everyone who is asked, every biochemist who is asked, what's the reason for the high solubility of globular protein in water? The immediate answer is that there are many hydrophilic groups on the surface. Now, about 15 years ago, more than 15, maybe 20 years ago, we examined that question following the suggestion of Harry Saroff. What we did is took several proteins and remove all the groups on the surface of the protein. If you remove all the groups, both hydrophobic and hydrophilic, you will get a huge hydrophobic ball, if you want, a hydrophobic ball. Now, if you calculate, you cannot measure the solubility, but if you calculate using the scale particle theory, you will get extremely low solubility, or you get the equivalent of the solvation free energy is some few thousand. I have the numbers here, about 4,000 or 5,000 kilocalories positive. Positive free energy of solvation is translation to minus KT or RT length solubility. Now, so if you have a huge hydrophobic molecule, its solubility will be 10 to the minus 100 or even less, maybe one molecule in all the oceans in the world. Now, the surprising finding was that if you put all the groups back to the protein, but distributing these groups at random, is this okay? Distributed at random, you don't get high solubility. In fact, you improve on the solubility,
but you don't get high solubility. So these are a few steps that were done. First of all, you take the hard sphere of the same size of the protein. Its solubility or the free energy of solution will be very large and positive. Now, if you put the solvent, the soft interaction, say, between all the hydrophobic groups with the water, you improve a little. This is number 2 here. Now, if you put all the hydrophilic groups at random distribution, you improve. Delta G goes down, which means the solubility will go up. However, you will not get the large solubility of the protein. Now, in order to get what we found, that in order to get the large solubility, it's not enough to introduce all the hydrophilic groups. There must be some specific distribution of the locations of this hydrophilic groups in such a way that water can form a hydrogen bridge between 2 hydrophilic groups. Now, each water bridge like that contribute roughly a factor of 100 to the solubility. And if you have many of these, this is only pairs of hydrogen bonding groups, but you can have triplet and quadruplet. So the reason for the high solubility is not only the number of hydrophilic groups, but more important, the distant distribution between the hydrophilic groups. Now, as I said, these are different stages of placing back all the hydrophilic groups, but if you go to the original distribution, you get a very large negative free energy of solvation, which can be translated into very large solubility. Now, this is a caricature of what you need in order to solvate. You need to hold pairs of hydrophilic groups rather than single hydrophilic groups. Now, I will briefly go into the three main problems of the what is considered to be the protein folding problem. One is the thermodynamic problem, or the stability. What factors make the protein stable? And originally, in the history, Pauling and others before the 50s or the 30s and 40s of the last century, Pauling thought that intramolecular hydrogen bonds are important. Then came, that's the whole history, came a series of experiments done by John Shellman, which indicated that direct hydrogen bonding, when they occur in water, cannot contribute much to the stability of protein. So Kautzman came with the idea of the original idea in 1959 about the effect of the hydrophobic effect, and the idea that hydrophobic effect is responsible for the stability, both stability and the kinetic, which I will talk in a moment, still survive until today. However, about 20 years ago, when I examined all the possible solvent-induced effects, I found out that hydrophilic interactions, both solvation, pairwise hydrophilic interactions, and triplet hydrophilic interactions are far more important. Now, this is the question of stability. What makes the protein stable compared to the random coil, which the entropy of which is much larger? Now, the other question is associated with Levitan, and Levitan asks what are the factors that, I think I have a quotation here from Levitan, what are the factors that speed up and direct the protein to fold very quickly into the final three-dimensional structure. Oh, I don't know why this goes on by itself. How I get back. Okay, so, and again, most people believed, I hope it will stay there, believed that both the speed and the specific direction or the pathway of folding is due to hydrophobic effects. And again, when we examine both the interactions and the force that one can obtain between two hydrophilic groups, we found out that the hydrophilic forces are much larger. Now, here is a simple question. If you see that two hydrophobic groups or two groups in, well, I want to stop that. That's, oh, sorry. I don't know, when I get to this, they go. So if they go, well, this is in water. If two groups get very fast to each other, and you ask what's the reason, the immediate thing is the immediate answer to that question is that there are some strong forces. Now, if you calculate the forces between two hydrophobic groups, you take the potential of mean force between, say, two methane molecules and take the gradient, you find that the forces are very weak. However, if you take two CO or two OH or two water molecules, like here, two water molecules approaching each other, at some distance there is a large force between the two, which is due to the possibility of hydrogen bonding, forming a bridge of hydrogen bonds. Now, the formula, the statistical mechanical, I don't know how to control this, that it will do what I want, not what it wants. So this is the statistical mechanical expression for the force. The first term is the direct force, that is between 1 and 2. 1 and 2 can be either hydrophobic or hydrophilic. And there is a solvent-induced effect, this is the force due to water molecule or any solvent molecule on 1, but times here the local density of solvent molecules, which is denoted by 3 here, given some configuration of the two particles. Now, this configuration of the two particles is replaced in the protein by the conformation of the entire protein. Now, one can calculate the potential of mean force between two hydrophobic or hydrophilic groups and take the gradient to get the force. I'm sorry. So there are 4 possible cases. If you have two hydrophobic groups, one hydrophobic, one hydrophilic, one hydrophilic and one hydrophobic, and the blue circle is a water molecule. So one can see even qualitatively, and this is confirmed by doing simulations, that here both the concentration. Remember, we had 2 terms here. We had the force, the direct force between a water molecule and 1, and we have the concentration of the water molecules given condition that we have 1 at 2 at some specific location and orientation. Now, in the first case, in the first case, what shall I do? In the first case, we have both a weak force and also low concentration, relatively low concentration of water molecules around this force. So we will have relatively weak force acting induced by the solvent. Now, if we have, again, a hydrophobic group here and a hydrophilic group here, the force that is exerted by the water molecule on this CH3 will be weak as here. This is shown by this arrow, the heavy arrow. But the concentration of water molecules will be larger because of this hydrophilic group. So the density, the local density, will be larger. Now, once you have a hydrophilic group here and a hydrophobic group, the density will be as here. On the other hand, the force exerted by a water molecule on the hydrophilic group will be much larger. Now, the last case, when you have hydrophilic groups, both in both sides, so we have both a strong force, direct force between a water molecule and the hydrophilic group, as well as a group which enhances the local density of water molecules. So this is schematically the order of magnitude which one can get also from a simulation of the forces between two hydrophobic or hydrophilic groups in water. So in a way, I will show you just schematically here when you have hydrophilic group, why you get fast, not only fast, and specifically directed pathway of the protein folding. And of course, there are some extension of this when you have interaction between a water molecule with two hydrophilic groups or even three hydrophilic groups, or in the environment you can have, I will show you some graphs in a minute, in the environment you can have both one, two, or three hydrophilic groups that enhances the density. So hydrophilic groups cause both stronger direct force between a water molecule and a CO or OH, as well as enhancing the local density around that group. I think this is the main answer to the Levitan question, which sometimes is called the Levitan Paradox. I never saw a paradox. Levitan himself never saw a paradox, but it became to be known as the Levitan Paradox. That Levitan originally estimated how long it will take to protein to find its way to the three-dimensional structure if it were to fold or to move randomly in the configurational space. And it doesn't do that, of course. It will take eons to do this random search of the final configuration. Okay, the next thing I want to combine the discussion of protein association with molecular recognition. Now, in molecular recognition, the main problem how a ligand find the best place to bind, or if you have two different sites to bind, the main explanation so far is due to the so-called lock and key model. That is where you have a perfect fitting. Now, when I say fitting, it could be either geometrical
fitting of the ligand, of the ligand to the site, or some kind of patterns of groups like plus and minus, or two groups that can form hydrogen bond. So in this case, the lock and key, it doesn't have to be geometrical fitting. It could be a pattern of some kind of functional groups that can that increase the direct interaction between groups on the ligand and groups on the proteins. Now, all this will change if we have, well, this is, again, dimerization of two proteins. I want to skip that. I want to get to the, I will come back in a minute to that. Now, geometrical fit per se is not the most important thing. If we have, for example, a ligand which is a sphere, and it is hard sphere, of course, the interaction will be zero no matter what is the form, even if it fits very well into this site. When we say lock and key, we mean that there is maximum direct interaction. Direct, I mean, between groups on the ligand and groups on the protein. So we have maximum interaction between, let's say, this ligand with this site, and similarly, maximum interaction between this ligand and this site. So if it were hard spheres only, of course there is zero attractive interaction, and therefore the key and lock model would not work. Now the whole thing will change. Well, this is for a pattern that I showed before. The whole thing will change when you have a solvent-induced effect, and more specifically when you have hydrophilic interactions of the type that I showed you before. You have two hydrophilic groups that can be hydrogen bond bridged between the two. So here is the, let me show you here, for example, you have two sites, A and B. This ligand fits better into this site rather than in this site. So if the binding were to take place in vacuum, the probability or the free energy of binding would be larger here than in this case. However, if there are two groups, two hydrophilic groups that can be water bridged by a water molecule, then this effect can increase the binding free energy by a factor of about between minus 2.5 to 3 kilocalories in favor of, well, again here, in favor of this configuration, or in favor of this site. So in liquid water, this site will be preferred for binding rather than this site. Well, this is for the, and of course, I talked about only one bridge. There could be bridge by a sequence of water molecules, or water molecule that can form 3 hydrogen bond bridge, which enhances the binding free energy. And in rare cases, it could be form 3 or 4 hydrogen bond bridge. Of course, if you form 3 or 4, you need to have the corresponding hydrophilic groups as donor or acceptor for hydrogen bonding. Well, this is kind of simulation of, again, this fits better to A in vacuum. It will not fit very well here and not here. However, if there is a possibility of forming a water bridge or hydrogen bond bridge, this site will be preferred.
Now, the same principle holds when you have two proteins. As I told you before, the mystery of protein-protein association is what compensates for the loss of the translational entropy of one protein when they combine when the two combine to form a dimer. And in the literature, in the old literature, you will find arguments referring to the hydrophobic effect. However, the hydrophobic effect is very small in this case, and the hydrophilic effect that are possible is that water can form bridge between two groups, each on different proteins. So you will have a kind of ring of hydrogen bond bridges. I think it shows here. Well, not here. Well, I think I had it before. Yeah, the bridge is here. The ring of hydrogen bond bridge around the two proteins, and each of these can contribute between -2 to -3 kilocalories. And if there are 10 of these, so you have a huge driving force for the binding. I would like to talk a little more. This is just a caricature of the forming a tetramer on possibilities of larger hydrophilic force. This is for the dimerization when you add more and more hydrophilic groups. I don't know if I should mention here this two isomers of decarboxylic acid, fumaric and maleic. Fumaric is the trans decarboxylic acid, and maleic is the cis one. Now, if the only reason for the solubility, large solubility of protein, was the number of hydrophilic groups, here we have the same number of hydrophilic groups. However, the conformation is different. And the difference in conformation results in different in solubility by a factor of 100 in favor of this. And my explanation is that in this conformation, you can form hydrogen bond bridge, which lowers the solvation free energy. Now, I don't know how much time I have to show you some extensions. This is a water molecule and one hydrophilic group and one hydrophilic group here. So there is a direct force between the water and a group on the ligand. And this hydrophilic groups enhances the density here. Now, you can extend this to having two hydrophilic group, which enhances more the concentration of water molecules, and then the water molecules interact either interaction in terms of potential of Mill force or the gradient or the force, or you can have one hydrophilic group and two hydrophilic group on the ligand. So you have larger force in these two cases, and you can extend this by taking into account triplet of hydrophilic groups that enhances the concentration of water molecule, and of course all the combinations of 2 or 3, in rare cases also 4, which is the maximum, of course, of hydrogen bonds that water molecule can form, and you can get higher and higher forces or interactions. I think at this point I will stop. You can have also, like in silica, you have a layer of hydrophilic groups that can extend something like the easy structuring of layer. I don't think it goes so far into the liquid, but one or two layers of water molecules that can be structure, or the structure in the sense that there is high probability or high density of water molecules that can interact with the ligand or the other protein. I think I will stop here, and thank you very much.